A routing protocol is the method that routers use to share and learn about routes from connected routers. There are many different routing protocols, each with their own strengths and weaknesses. To understand their differences, let's look at how routing protocols are classified. The first way of classifying a routing protocol is the scope. The scope identifies what information is shared and remembered. A private network that is connected to the internet is known as an autonomous system, or AS, and is fairly independent from the internet. The only thing that is really shared is the link to the internet. Businesses or organizations that connect their private network to the internet are assigned a unique autonomous system number, or ASN, which is typically handled by the ISP. Now, the routing protocol scope identifies boundaries where routing information is shared. An interior gateway protocol, or IGP, is a routing protocol that is used within an autonomous system. So within your private network, you would run a routing protocol to share internal routes. This is an interior gateway protocol. An exterior gateway protocol, or EGP, is used to share routing information between autonomous systems. So for example, a routing protocol used within the internet to route data between internet routers and into autonomous systems would be running a routing protocol that is classified as an EGP. As a network administrator, you will mostly work with IGP routing protocols. The only situation where you would work with EGP is if you had a very large network connected to the internet. Another way of classifying a routing protocol is how it makes routing decisions based on a specific metric. The metric is a value assigned to the network that identifies the preferred route when multiple routes exist. A route with a low metric indicates the best route. One metric used by a routing protocol is called the hop count. Now, the hop count identifies the number of routers that are used to reach a destination network. So, say this router has a message that needs to be sent to the D network in this direction. The hop count to the destination would be 1, 2. The packet goes through 2 routers to reach the destination. If the packet traveled this direction, the hop count would be 1, 2, 3. In this example, this router has 2 routes to the destination network. If using the hop count as its metric, it will use the path with the lower hop count, which is the one with 2 hops. Another metric that can be used is a metric based on the bandwidth, or sometimes latency or delay. These both measure how fast a message is sent from the source to the destination. Let's say that this router here has 10 megabits per second links. And these routers down here all use 100 megabits per second links. In this example, it would be faster to send the information this direction rather than across the slower links. If the routing protocol was using the hop count, it would prefer this route to the destination, even though it's slower. But when using the bandwidth or delay as a metric, each link is assigned a relative cost value. For instance, let's say these 2 links each have a value of 100, so the total cost going this direction to the destination would be 200. Now, down here, each of these links may have a metric value of 10, meaning that going this direction would only have a metric value of 30. In this case again, the lower metric wins, so this router would use this direction when sending the information to the destination network. These values that are assigned based on bandwidth or latency are typically identified based on the routing protocol. For example, the routing protocol might say all 10 megabits per second links get a metric value of 100. And there may be even more complex computations which actually take into account the delay that happens when sending real traffic between the 2 routers. The basic idea is that the routing protocol tries to calculate the bandwidth and the delay and assigns the link a value that helps identify the best path. Another metric that can be used is a relative value. With this, every link might be assigned a default value. An administrator could then change these default values to manually control traffic flow. If the routing protocol used one number for all links, regardless of the bandwidth or delay, the routing protocol would be using the hop count. But an administrator could go in and modify the values on each link, increasing or decreasing these values in order to customize how data flows through the network. This relative value that is assigned is often called a link cost and can be based on a number of ideas. Another way to distinguish between routing protocols is the method used to share routing information. The first method is called the distance vector method. With the distance vector method, every router shares its entire routing table with its immediate neighbors. Let's take a look at an example. Before the routing protocol starts, each router would have routing table entries for the directly connected networks. The first router would know of networks A and B. This router would know of networks B and C, and this router would know of networks C and D. Routing information is shared by routers periodically. So first, this router would share the routes it knows about with its neighbor. In this case, it knows about routes A and B. The second router receives this information and looks at its own routing table. It sees that it already knows about network B, but it doesn't know anything about A, so it would add A to its routing table. Let's also assume that this routing protocol is using the hop count metric. In this case, directly connected networks are identified with a metric of 0, meaning that there are no routers that have to be traversed to reach the destination network. When the first router shares its information, it will share that it knows about a specific network. The router, in adding the new network to its table, would know that the route is not directly connected, so it would take the information that it shared and then increment the hop count by 1, knowing that in order to reach the destination network of A, this router must go through one additional router to reach that destination network. Now let's say it's the second router's turn to share its information. It would share routes with each of its neighbors, so it would share with this router as well as sharing back with this router. The routing table that's sent to this router would contain the entries of B, C, and A in its routing table. This router would say, I already know about network C, but I don't know yet about B. It would then add B to its table and increment the hop count, and it doesn't know about A, so it adds A to its routing table and increments the hop count. When the routing table from the second router gets shared back, this router does the same thing. It already knows of networks A and B, but it does not know about network C, so it would add that to its table. After this, the third router would share information back with its neighbors. The middle router receives this routing table from its neighbors and identifies a network that does not yet exist in its routing table and adds that information. Now, this first router still hasn't learned of network D. It isn't until one last update from the middle router to its neighbors that the first router will learn about network D and increment the hop count. At this point, every router knows about every network, so we can say that convergence has occurred, meaning that all routers share a consistent view of the network. A key characteristic of the distance vector method is that every router shares its entire routing table with its neighbors at every update interval. Another method is called the link state method. With the link state method, routers only share information about their own directly connected networks. So for instance, this router would share information about networks A and B. It uses special messages called link state advertisements, LSAs, and link state packets, or LSPs, to share information throughout the network. When a router receives one of these advertisements from a router, it records the information in its own routing table and then forwards that same information onto other routers within the network. So in this case, the advertisement that has come from the first router about networks A and B would go on to the second router and then be forwarded to the third router without any modification to the information. Likewise, the second router would share information, each direction, about its connected routes, advertising that it knows about networks B and C. And finally, the third router would do the same, sending information about networks C and D to its neighbors, which would then forward that information on throughout the network. The process of sending LSAs and LSPs through the network is called flooding because a single packet is flooded or forwarded throughout the entire network. Routers use these advertisements to build a database or a topology of the network within its own routing table. Eventually, each router will learn about every other network. Once convergence has been reached and all routers know about all of their networks, these advertisements would contain only changes instead of all directly connected networks. The main differences between the distance vector and the link state methods are that with the link state method, routers only share information about their own routes with their neighbors, and these updates are passed along between routers. In addition, once convergence is reached, routers only share information about changes, not all known networks at every update. A third method used to share information is called a hybrid method. As its name suggests, it combines the distance vector and link state methods. One final method of classifying routing protocols is their support for variable length subnet masks, or VLSM. VLSM allows routers to use subnet masks that are different from the default. For example, if you have an address of 10.0.0.0, the default subnet mask is 255.0.0.0 or indicated with a /8. With a variable length subnet mask, you can use a custom mask and subdivide this address into multiple subnets. For example, you can use a non-default mask to create smaller subnets. Early routing protocols relied on the default subnet mask when sending routing information. When a router would advertise a no network, receiving routers would assume that the default subnet mask was being used. This caused a lot of problems. For example, say you have 3 networks connected by routers, and say this network uses a custom subnet mask separated by another network and connected to a third network here. When this router advertises this route with its neighbor, if it did not support variable length subnet mask, it would simply advertise that it was connected to network 10.0.0.0 and not include this information here in this octet because this is not part of the default subnet address. And this router would advertise this route to its neighbor. Now let's say that this router has a packet that is addressed to 10.1.1.1. When it goes to send this information, it will look in its routing table and it would not find an entry for this network. In fact, if this router only understood default subnets, it would think that it was connected directly to the same network out this interface. So when it received a packet addressed to this address, it would think it resides on this subnet somewhere. With variable length subnet mask, routers are able to advertise the subnet mask along with the subnet address. So in this case, this router would advertise a subnet address of 10.1.0.0 with a subnet mask length of 16 bits. This router would then have an entry in its routing table for that destination subnet. When it receives a packet addressed to that subnet, it would know that it needs to be sent this direction. Virtually all routing protocols today support variable length subnet mask. Only early protocols use the default address class. Routing protocols that do not support variable length subnet masks are called classful routing protocols. Address class is used to identify the subnet mask. Protocols that do support variable length subnet masks are called classless. The address class is ignored and the subnet mask is included with the routing information. Well, that's it for routing protocols. In this lesson, we learned about the different ways to classify routing protocols. A protocol can be classified by the scope of information it shares, by the metric used to distinguish routes, the method used to share routing information, and whether or not variable length subnet mask is supported.